All right, welcome back, everybody. So I'm excited to introduce our, I guess, the last speaker of the regular program for today, although there is still another special talk after the reception. So we're very lucky to have Rachel Zhang from MIT here to tell us about binary error correcting codes with minimal noiseless feedback.
Thank you, Mary. Yeah, this is joint work with Mego and Venkat, who are awesome people back there. But yeah, okay. So I guess there's like two things I want to tell you about. So first is error correcting codes, which you guys should probably know. Second thing is feedback, which you might be a little bit less familiar with, but we'll talk about it too. So maybe let's start just with error correcting codes. So what's the job of error correcting code? Well, Alice might be trying to send some message to Bob, right? I mean, if there's no noise, she can just send over the message and then they're all good. But what happens if the channel is noisy? In particular, suppose some of the communicated bits are corrupted. Then now Bob can't necessarily correct to Alice's version of the message perfectly. So I guess the question is can Bob still learn Alice's input X if an adversary Eve corrupts some of the communicated bits? And we all know the answer is yes, right? So what you do is you use an error correcting code, and Alice is going to send an encoding of her message X instead of just her X in the clear. And as long as this error correcting code has some good minimum distance property, so every two code words are sufficiently far apart, then even if up to half the distance of errors occur, Bob can still round to the nearest code word and figure out what X is supposed to be. Okay, cool. So the second thing I want to tell you about is feedback. So I guess feedback is really quite a natural phenomenon. It's the idea of if you're sending information out into the world, you're also getting information back, right? I'm giving this talk right now. I can see your faces. I can tell if you're paying attention, if you care, if you are listening. So another example, for instance, is a kid with a robot. You might be sending instructions out to the robot. And based on what the robot does, which is the feedback you're receiving, you might then choose adaptively what you if the next instructions, what the next instructions you're going to give it are, right? So it's really this process of feedback is able to kind of help you learn, figure out what to send next. And I want you to apply this notion of feedback to this something of error correction. So a question you may ask is can you actually, so I guess okay. So the question I want to ask is, can you use feedback to improve error correcting codes? Okay. Unfortunately, the answer is no, at least if you care about capacity. So if you care about random errors and you just care about capacity, you actually can't increase capacity or the rate of communication using feedback. What you can do, though, which Berlekamp showed in 8 years later, is that actually feedback can improve your resilience to error. Okay. So I want to tell you a bit more about this result. So what did he show? Well, let's start first of all with just a standard error correcting code model. So standard error correcting codes are a one-way communication model. There's no feedback involved. And the guarantee for binary codes is that as long as less than 1/4 of Alice's bits are corrupted, then Bob is guaranteed to learn X. Right? This is just because binary codes have minimum distance 1/2. Okay. What about feedback codes? Well, maybe first of all, what are they? So feedback codes are this model where so it's an interactive protocol, right? So Alice is able to send forward information, but at the same time, she's going to receive feedback back from Bob about what he's received. So usually we'll think of this as a fixed round, fixed speaking order sort of protocol. So the speaking order, the way they're going to communicate is fixed in advance. And one way you should think of the feedback is really a way for Bob to tell Alice what he's received, so that she knows her state at every point in time. I want to emphasize that Bob's feedback is considered to be noiseless. So whatever Bob knows, Alice will learn. And also, when you consider error resilience and the ability of the adversary to corrupt bits, we're not going to. So Bob's feedback will be excluded from what the adversary can corrupt. So when you count the corruption budget, it will be the adversary can only corrupt the four yellow messages, and the corruption budget will be measured as a fraction of the yellow messages sent. Okay, so what did Berlekamp show then? So the result is, so instead of 1/4, which is just for the one directional communication setting, he showed that as long as up to 1/3 of Alice's bits are corrupted, then you still get the same error resilience guarantees. In some sense, it's 1/4 to 1/3 shouldn't be so surprising, right? Because what's happening is Bob is able to use his feedback to ask Alice like specific questions about what he needs to learn to get the most relevant piece of information from Alice at every point in time.
And this was random error?
No, this is adversarial errors. Yeah, so everything I'm going to talk about is going to be adversarial errors. Yeah.
Is the number of rounds bounded?
Yeah, I think you should usually think of like the description of the protocol will be like, there's an n round protocol. Some rounds are going to be from Alice, some are going to be from Bob. They're determined in advance which ones are from Alice, which ones are from Bob. The length of the protocol is fixed, and then you want to consider like the error resilience of this protocol. When I say 1/3, I really mean 1/3 minus epsilon. So the number of rounds will grow with like 1/epsilon also.
For this result, I think you only need one round, right?
For
Berlekamp's result.
do you have to 1/3? I don't think so. I think you need to grow a number of rounds, and we'll show that also actually. But you can do better than 1/4 with just one round if you can.
In Berlekamp's result, is there a bound on how much Bob can talk, or Bob is allowed to?
Yes, that's a great question. Let's go to the next slide maybe, and then we'll see that. Any other questions about the model, I guess, before we do that? Cool. Yeah, so some comments. So first of all, so traditionally people study Bob's feedback as being continuous. So in particular, it's sent after every single bit that Alice sends. Okay, so what does this mean? Well, if Alice is trying to communicate a k-bit string, this means that Bob will have to send k rounds and k bits of feedback. Okay, that's quite a lot actually, right? Because first of all, interaction is quite expensive. Ideally, you want fewer rounds of interaction. Otherwise it's like a sort of like a degree when to talk and so on. It's kind of difficult. Another thing is, k bits of guaranteed noiseless communication is also quite difficult to ensure, right? Like you want to kind of minimize the amount of I guess basically this idea of noiseless feedback is kind of a strong consideration. And we'd like to see if we can minimize the number of bits of feedback that you have to send under this strong model. So the question I want to ask today is how much feedback do we actually need? Do we actually need these k rounds and k bits of feedback, or can we do better? Perfect question. Okay, so what do we do? So we answer this question. So okay, on the positive side, we can show that there exists an error correcting code with feedback where Bob only sends log k bits of feedback over constantly many rounds. And this is resilient to the full 1/3 fraction of corrections to Alice's bits that was known in Berlekamp's result with unbounded amount of feedback.
What depends on epsilon?
Good. Okay. It's a polynomial dependence on over epsilon. I don't remember exactly. It's probably cubed or forced or something like that. Number of rounds. Okay, I don't remember off the top of my head. It's some polynomial. I want to say 1/epsilon cubed or epsilon forced. But that's a good question. Also, if you can improve that. So I don't know.
And by this you mean there's a positive rate you can transmit it. Is that what you
Yes. Okay. So theorem 2. This is tight. So actually, if Bob sends fewer than log k bits of feedback, then Alice's best strategy essentially devolves to just sending an error correcting code. So you do no better than just 1/4. And the third thing we show is we can ask a question can you get this 1/3 with 1/3 error resilience with just one round of feedback, with 2 rounds of feedback? And we show no. The answer is no. You actually need growing number to approach 1/3. I don't remember exactly what our trade-off is. And I don't think it's tight either. But you do need it more than any fixed bounded number of rounds to get up to arbitrarily close to 1/3. Any questions?
Is there any advantage in Bob sending? So you're showing that order log k bits is sufficient. Suppose Bob is allowed to speak more. Do you get any further advantage?
That's a good question. So I mean, I guess Klim was suggesting maybe some of the epsilons could be improved. I'm not quite sure. Yeah, so maybe up to the epsilon factor is no, but possibly there's some epsilon factors you could gain.
How far is this from the capacity? In the Banner case, we know the full capacity.
Yes, I also don't know. It's probably not tight. One of the issues is when our result is going to rely on. Well, okay, I guess one capacity is a kind of weird thing because it usually seems random errors, right? But also our construction will rely on error correcting codes. And so like if you don't know the dependence for like error correcting codes, and you also don't know the dependence here, although you could ask like up to the error correcting code like dependence, can you know the trade-off? And I don't know either.
Capacity for channel feedback is known. Like unlike regular codes, for channel feedback is known.
Okay, cool. Okay, so this is for the case for the error setting. So log k bits of feedback over constant min round suffice. For erasures, we show a similar statement. So we show that, again, there's an error correcting code as feedback for the erasure setting, in which Bob sends only log k bits of feedback over constantly many rounds. This is resilient to 1 minus epsilon fraction of corruptions to Alice's bits, which is like also the correct bound, I guess. Yeah, for amount of feedback. And we also show this tight. So I guess for this remainder of the talk, I want to tell you a bit about the construction of these feedback codes and how they work. I want to start off with the erasure setting, just because it's simpler, and then we'll kind of go through some of the ideas that will be relevant for the error case as well. But maybe the erasure case is to start. Okay, so let's say there's no constraints on feedback right for now, so you can have as much feedback as you want. How do these feedback error correcting codes for erasures work? Well, the way it works is Alice is going to have a string that she wants to send to Bob. And what she's going to do is she's going to try to send her string to Bob bit by bit. So she's going to send 0, 1, 0, 1, 1. If Bob receives her bit, he's going to respond with a check mark saying, yes, I did get your bit. Now can you send the next one? If he doesn't get the bit, then what was erased, he's going to send her, no, I didn't hear it. Can you send it again? And she's going to repeat it again, the bit that she would try to send and didn't manage to send. And the point is, as long as there were k bits that were actually successfully sent over the channel, then Bob will have learned Alice's input. Okay. And so like if you make the length of the protocol like k over epsilon, then you get 1 minus epsilon error resilience. Okay, great. Okay, so now this is a lot of feedback though, right? This is k rounds of feedback, k bits of feedback. How do we do better? Well, there's this idea from error correcting codes called listed coding. The idea is basically there's a code where if you're given a single code word, as long as not too many fraction of bits are corrupted, so as long as fewer than 1 minus epsilon fraction of bits are erased, then there's actually a small list of code words such that X is guaranteed to be within the list. Okay, so how do we use this? Well, what you can do, so Alice wants to send X to Bob. She's going to start off by sending an error correcting code of X. Okay, the hope is for Bob to list a code to reduce the problem to a smaller number, a smaller list size. Of course, like if this doesn't have the guarantees, so if there's too many that are corrupted, then all bets are off. So what Bob is going to do is just send like, oh, I didn't get that. Can you send it again? She's going to try to send it again. When Bob finally does receive this code word and is able to list a code to a small list of possible code words, now what they can do, so now Bob knows that X is one of these 1 over epsilon many options, right? If he's able to tell Alice these 1 over epsilon many options, then Alice just has to help him decide which of the 1 over epsilon many options her code word actually was, right? And we already saw a protocol in the earlier slide to transmit like k bits over k rounds. So over here, now we just have to do a 1 over epsilon round interactive protocol for Alice to tell Bob which of the 1 over epsilon options her code word actually is. So this is a constant round protocol, so that's much better. Okay, but maybe let's look at Bob's like actual like feedback complexity. So I mean, this is cheap, right? But what about like this? That's 1 over epsilon code words. Each one is k bits long. That's not so good, right? So that's an issue. So that's still going to be O of k bits. So we're halfway there, but we're not quite there yet. Okay, but actually, so Bob has to learn one of these like 1 over epsilon code words, right? But he doesn't actually have to tell Alice these full code words. What he can do is just send her enough information for her to help him decide which of the 1 over epsilon code words he actually is, right? So he just has to send enough information to distinguish between them, not actually to specify them completely. So let's see how this works. So instead of sending these 1 over epsilon messages, what he can do is he can send 1 over epsilon indices, I1 up to I1 over epsilon, on which these 1 over epsilon code words differ, as well as the values of the code words on those indices, right? And this will be enough information for Alice to figure out which of the 1 through 1 over epsilon her code word actually corresponds to, and then the rest of the protocol communicating that code word back to Bob.
By
would there be such indices? Why would there be such indices?
Yeah, it's a good question. So if you have like 1 over epsilon different strings, what you can do is you can kind of just like, maybe find one index on which like, yeah, like maybe like half of them are different or something, and then pick another index on which you can differentiate 2 more. I guess at every point in time, as long as you can differentiate one code word from the rest of them, then you can find such a set. Actually, 1 over epsilon is not tight. I think you can do log 1 over epsilon, but 1 over epsilon for simplicity.
And I suppose at this point, there are only errors seen after that. Is that a possibility?
Only errors after this.
Yeah. So meaning Alice, no more of messages of Alice go through.
Yes, so you'll have to, yeah, so I guess in the actual protocol, you'll do this thing where like, it's gonna be a very long protocol, and Bob will send this like ECC for a while, or like, sorry, Alice will send this ECC for a while. At some point in time when Bob can list the code, then he'll send these options over. And like, the point is now if all the rest of Alice's messages are erased, that's too expensive for the adversary. So they'll have to have corrupted 1 over epsilon for a lot of the rounds earlier, for which Bob didn't receive the code, and then also everything else
It's
there.
a constant factor loss in the rate, which we're not measuring anyway.
Yeah, it's like 1 over epsilon, yeah.
Sorry?
Mm-hmm.
So why does Bob even need to send the evaluations of the 1 over epsilon code words in the 1 over epsilon indices? Like, why isn't it enough to just send the indices and then Alice just tells him what are the values in this?
Yeah, that's also probably reasonable. You can also do that.
Okay.
All right, great questions. Anything else or seem okay? Perfect. So that's the erasure protocol. Oh yeah, so this is the erasure protocol. Again, the list coding paradigm. Bob sends enough information for Alice to help him decide which of the 1 over epsilon options he actually that she actually has, and they communicate over a fixed, like a constant number round protocol for her to tell him a number between 1 and 1 over epsilon. Okay, now let's go to the error setting. So again, for the error setting, we have, okay, yeah, just like error correcting code is feedback with log k bits of feedback and constantly many rounds. And it's related into up to 1/3. Okay, so let's begin again with list coding strategy from the previous, from the erasure setting, right? So again, what's basically happening is you have an error correcting code. Error correcting code is just a bunch of points in space, right? And suppose this is the code word that Bob actually receives. Well, they can draw a circle of radius n over 3 around this point, and only the code words that are inside this ball are like sort of possible options for what Alice could have had. And the point is, like list coding basically tells you most code words must be quite far away. So only very few are remaining inside the ball. And so now if Bob could just send Alice these closest strings, and Alice could have him distinguish between them. But unlike the erasure setting, we can't forget about far away strings like in the erasure case. The erasure case, once they've exited the ball, we know that they can no longer be a possibility, right? Because the erasure has happened, or like, you see a bit that's inconsistent with one of these outside strings, so you know they can't be the actual string anymore. For the error setting, early on in the protocol, maybe some strings have gone kind of far away, so they seem more unlikely, but that's only the beginning of the protocol, right? So the rest of the protocol, they may come back into relevance again. So you can't actually forget about strings like you did in the erasure case. So we're going to do something more clever. So instead, what do you do? Okay, so I want to introduce to you a coin game. So what is a coin game? Where, well, it's not really a game. It's more just like some coins on a number line. But basically, it's going to be a bunch of coins corresponding to each of Alice's possible inputs. At the beginning, they're all going to be on this number line throughout the game. And their position at any given point in time is going to be equal to the number of corruptions witnessed so far if Alice actually had input equal to that coin. So at the beginning of the protocol, they're all going to be at position 0 because no bits have been transmitted yet, right? So no corruptions could have occurred yet. But after one round, maybe Bob receives a 1. That means that all the coins that correspond, for which Alice would have sent a 0, now have seen 1 corruption, right? And so for all those coins, they're going to move up by 1 in the number line at time 1. Okay.
Different coins represent the different messages that.
Yeah, the different values that Alice could have had. So there should be 2 to the k of them. Yeah, and then at time 2, maybe Bob receives a 0. So all the coins which correspond to Alice would have been sending a 1 should now move up by 1. And so we'll kind of keep going as throughout the protocol. Okay, and so like this will keep going. This will keep going throughout the protocol until some coins will fall off the board. How long is this board? This board is going to be length n over 3. once a coin has fallen off the board, that means there's too many corruptions have occurred, so they can no longer be a possible valid input for Alice. Okay, so as long as there's only one coin left on the board by the end of the protocol, then Bob can figure out that's actually what Alice's message was supposed to be. Okay. The adversary's goal, on the other hand, is to keep at least 2 coins on the board by the end of the protocol. In that case, the adversary wins. Bob can't distinguish between the 2 possible options for Alice's input, and then they're very sad. It's okay. So I guess like the main point is that this is, yeah, it's kind of a different thing where like you actually don't care what Alice's message is, but you just, but like it's just like from Bob's point of view, simulating like this, like where every single like which of the possible like inputs are valid at every given point in time.
Yeah. So I should imagine this is literally how Bob's trying to decode Alice's message, essentially. Okay.
So using this coin game sort of like paradigm, I want to tell you about this protocol by Spencer Winkler from 1992, which achieves 1/3 error resilience at the cost of many rounds of feedback. So this protocol is actually quite simple. So let me just tell you how it works. So yeah, so once again, it's a very interactive protocol. So after every bit that Alice sends, Bob is going to send feedback telling what he received. And so basically, both Alice and Bob know the state of the entire board at every given point in time, right? Because Alice can simulate what Bob knows by knowing what he received. Okay, so now how does Alice choose what to send? Well, she's going to order all of the possible inputs according to their position on the number line. And she's going to tell Bob whether her input was an odd or even rank. Okay, so that's either 0 or 1, corresponding to, you know, if the coin that she actually has is one of the odd numbered ones or one of the even numbered ones. So for instance, if Bob receives that Alice had an even numbered coin, he's going to take all the odd numbered coins and move them up by 1. Okay, and then after this one step, both Alice and Bob are going to renumber the coins, reset the protocol, and do the same thing again. Okay. And it turns out this is a complete protocol, and this actually gets you up to 1/3 error resilience, of course, with many rounds of feedback.
So the numbering was from left to right.
Left to right, yeah, smallest to largest. Okay, so I'm not going to tell you why this protocol works because the analysis is quite involved. But like sort of the magic equation that kind of describes why things are working is the following. You can show that as time goes on, the sum of the position of the first 3 coins will be at least a number of rounds, roughly, like plus a little bit, plus or minus a little bit. And if you know this is true, let me tell you why you're done. So at some point in time, because you know the total number of rounds is n, and your board is only length n, the 3rd coin will fall off the board. I'm going to say after r rounds. After this point in time, the first 2 coins, well, Alice is either going to say odd or even at every single point in time, right? So one of the coins will always be moving up by 1. So after this point, the first 2 coins positions will always increase by 1 total. This means that at the end of the protocol, so the sum of the first 2 coins, well, up to round r, their positions were at r minus n over 3. And then after round r, they've increased by n minus r more. And so in total, that's their total sum of their positions is at least 2n over 3. And then now if you just do an averaging argument, you see that at least one of them has to be at least n over 3 as well, which means that only one coin can fit on the board. So that's Spencer Winkler protocol. Yeah, it's a very simple protocol. I think it's kind of magic, but it's also very, very nice. So.
Yeah. And the proof of the magic equation is difficult to say.
It's not so straightforward. I don't think I have enough time to like tell you today, I guess. So, okay, so some comments. So first of all, again, Bob is going to send feedback after every bit. So it's a very interactive protocol. So this is going to take k bits of feedback. Okay, even worse, Bob actually needs to send enough information for Alice to know the location of all the bits, right? Because they need to mostly just simulate the entire coin game, so that she needs to know actually like what he's received, so that they can like agree on the state of all the coins. So that by itself is like in some sense going to take at least k bits. Like you could try to do something where Bob is sending the state of the coins. That's going to take 2 to the k. So really k is kind of the best you can hope to do in this setting. Okay. So that's not so good. What we really want is log k bits of feedback, right? So what are we going to do? Well, here's an idea. What if instead of playing Spencer Winkler on the entire state of the board, we only play this game on the first, maybe 10 bits, 10 coins, right? Because now if you play on 10 coins, your dealing with much fewer bits of information, perhaps you can, perhaps something will work. So the idea is, let's do Spencer Winkler on just the first 10 coins. Of course, again, we cannot send full k-bits for each of the coins. So we're going to send sort of compressed information, saying the indices as well as the values these indices, as well as the values these coins take on those indices. Okay, and this information here is going to divide all of the coins into a bunch of sets. So of course, so these sets are going to be corresponding to one set for each of these coins. So each of the first 10 coins are going to be in a different set. Outside of this set, different coins may be associated with each of the first 10 coins. So here's an example of how these coins might be partitioned. And so in general, as you're playing this coin game, what's going to happen is, for instance, if coin 10 is supposed to move, then all the other coins with the same color are also going to move by 1. So it's really you're grouping these coins into sets, and each set is going to move independently, one by one. Okay. So again, this is the magic equation. Yeah. Yeah. Oh yeah. So the sets are defined by the indices I1 up to I(1), and also the values that Bob is going to tell Alice that the first 10 coins that is take on those values. So sometimes these indices will be spread. If 2 coins take the same values on those indices, then they'll be in the same set. Okay, so again, the magic equation is the following. We want the sum of the first 3 coins positions to be growing with the number of rounds. So does this protocol satisfy this equation? Well, kind of. Assuming that these larger coins, the ones past the first 10 coins, are kind of far away from the first 10, then the first 10 coins do satisfy this coin game, right? Because they just are not relevant if they're far enough away. So sort of in the case where these coins are far enough away. But the issue is you can't always hope for these coins to be very far away. In particular, one of the issues was just playing this game. Okay, let's even say they're even already far away. An issue that can arise is these large coins actually don't really move enough. In particular, what can happen is for coins in the set S1, so corresponding to the red coins here, this first coin is not going to move very much because it's the one that has received the least corruptions. So these coins also will not move very much, right? And at first, maybe they're far enough away that it doesn't matter because they're not really they're not close enough to really matter for this decoding. But as time goes on, eventually they may come back into relevance. And by the time they come back into relevance, they haven't moved nearly enough throughout the protocol, and you're kind of screwed at that point. Okay, so here's an idea. Let's separate out coins in this first set S1. Just instead of having all of them kind of travel together as one pack, what we're going to do is actually they will all be spread out a little bit so that they actually only one of them can ever move 0, and the rest of them have to move a little bit at every point in time. Okay, and this turns out to be enough. So let me just tell you, I guess, what the protocol is. So Alice is going to send one of 3 things based on which of the sets her input is in. So she's going to send an error-correcting encoding of her input x if x is in the first set S1. And this encoding should have the property that has distance 1/3 between every pair of code words, so separate out words in S1 enough. If x is in one of the sets S2, S4, one of the even sets, she's going to send a specific code word M2. And if it's in one of the odd number sets besides S1, she's going to send a third code word M3. And what we'll need is these different sets of code words to have distance 2/3 between any pair of them. So if a code word is in S1 versus S2, they should be 2/3 apart and so on. Yeah.
Sorry, wait, just make sure. So the first bullet point is saying that between any 2 points x and x prime that are in the set S1, their encodings are distance 1/3 apart. But that may not be true. So it's not true for all 2 decay messages. You're saying with error correcting code. Or is this an error correcting code that's defined on all 2 decay messages, or just on the messages in S1?
It's only defined on the messages in S1, but I think if you define all of 2 to the k and then just forget about the ones that aren't relevant.
Okay, sure. Also. I see.
It's slightly worse rate, but.
Okay, sure.
Okay. So what does this protocol have? Well, first of all, we can show locally that the sums of the first 3 positions is always growing the number of rounds, as long as sort of large coins are far enough away already. And furthermore, these large coins are going to move enough, so that's fine too. Okay, so this seems like a pretty reasonable protocol. It works as long as large coins are far enough away. The issue is that we need to assume that the first 10 coins are actually separated out from the rest of them. So this only works if large coins are far enough away. Okay, so that's not so good. I mean, so it's kind of good. We have a protocol that works in some cases. But how do we get to a state where the large coins are far enough away? Okay. Well, we can just use error correcting codes. So recall again that error correcting codes have this list decoding property that for most code words, they'll actually go very far, right? Like they're separated out very well, except for a very few number of code words. Okay, so now we have two strategies. So strategy one is this modified Spencer-Winkler protocol on like the first O of 1 coins. And we have this magic equation that we wanted, so that's good. But it only works if large coins are separated out far enough away, so it's only very few close coins. Strategy two, error correcting codes, will allow us to get to a condition where strategy one will work. So in strategy two, the error correcting code, it will actually send most coins far away. Of course, we don't have any control over the close coins, but that's strategy one is going to be able to do. So in some sense, we have two protocols, two strategies, which both have their own weaknesses, right? Like one only works if it's, large coins are really far, but it has other properties you want. Strategy two, like you can't do anything about the close ones, but it allows you to get to a point where strategy one will work. And that's our protocol. So our protocol is going to work as follows. So you have constantly many rounds, split it over into constantly many chunks of rounds. Each round, you're going to adaptively, based on sort of what the coin game looks like, do one of the following. You're either going to do the modified Spencer-Winkler strategy on the first O of 1 coins, or you're going to do the error correcting code strategy based on how far away like a large coin is from the third coin. Okay. Yeah, so that's our protocol. And you can show it works. So yeah, so this has log k bits of feedback, of 1 rounds of interaction, and I guess you want 0 errors. So I just wanted to conclude with, okay, I guess first of all, this work, we managed to get log k bits of feedback over constantly many rounds of interaction. Okay, so some open questions. I think there's a lot, by the way, which is why I wanted to talk a bit about this. So, so question one, okay, so our protocol is a deterministic protocol. Our lower bound is only also for deterministic protocols. We don't really know what the correct answer is for the randomized protocols, whether you can do fewer bits of feedback or not. We think the answer is yes. But we weren't able to show it. So I think that's kind of interesting. Another question is like, can we get sort of exact trade-offs between the number of rounds and error resilience, or the number of bits and error resilience? The first question was studied a bit by work by Braverman, Efremenko, Cole, Saxena, Zhang. Right? Okay. Did I mess up one of the words, or one of the names?
Saxena and Zhang.
Okay, so some people wrote this amazing paper. Yeah, so I think it's quite an interesting question, and I think you've also alluded to the question of like determining sort of the epsilon versus like number of rounds versus number of bits trade-off exactly in terms of epsilon. Also, don't know the answer to that. And finally, like, so the entire talk has been based around the notion of the feedback being noiseless, right? But you can ask the question like, what happens for noisy feedback when the feedback is actually corruptible? And recently, we've had some partial answers to this question. So in particular, for one particular answer to this question, come to Klim's talk tomorrow. So yeah, that's all I had to say.
So randomized protocol means only local randomness?
Yeah, I think in general, you don't want shared randomness because then you can do like very silly things.
Were these protocols efficient?
Yeah, I think so. Obviously, polynomial time decoding. I think really the main cost is like. Oh, actually, no, you're right. Yeah, I think maybe keeping track of all the coins will be kind of expensive. So yeah, you're right.
So by noisy, that do you mean adversarially noisy, governed by the same matrix?
Yeah.
Let's thank Rachel again.